Under the wave subtopic, good morning students. Under the wave subtopic, today we will discuss and talk about the periods, angular frequency and the frequency. So starting from waves, and angular frequency. So first of all, draw a figure under which we have sinusoidal wave. On the x-axis we have time component t. On the y-axis we have displacement component. Okay. So now if there is a sinusoidal wave such like that, then here if it is consider a particle at this position at time t1, okay, at time t1. Now here we have amplitude a. Now let us suppose at t2 this particle has the position such like that here only. Now here we can say the same particle or the two different particles are in the same phase. So the distance between this t1 and t2 timings are known as time period capital T. So first of all, labeling the graph. A graph of a, this is the above is the graph of the displacement of the string element at x equals to 0 as a function of time. As the sinusoidal wave of this figure passes through it, the amplitude A is indicated. A typical period t measured from an arbitrary time t1 is also indicated over here. The graph of displacement of the string of the string element that as a function of time as the sinusoidal wave passes through it the amplitude A is indicated. A typical period t measured from an arbitrary time t1 is also indicated over here. T1 is also indicated. The above graph shows the above graph shows the displacement y of equation yxt a sin kx minus omega t plus phi. The above graph shows the displacement y of equation this versus time t at certain position along the string taken to be x equals to 0. Now if you monitor the string, you would see that the element of the string at that position moves up and down in simple harmonic motion, and that will be given by in the above equation by putting x equals to 0. So if we closely monitor the string, we can see that we can see that the element of the string at that position moves up and down in simple harmonic motion, moving down in simple harmonic motion, given by equation suppose this is equation 1, given by equation 1 with x equals to 0. Now y is equal, by putting the x equals to 0 in the equation 1, what we have a sine minus omega t, and sine minus theta is always minus sine theta, so this will be now the above figure shows, so suppose this will be a figure 1. Figure 1 is a graph of this equation. The above figure 1 is the graph of this equation. It does not show the shape of the wave. It does not show the shape of the wave. The period of oscillation t of wave, t of a wave is defined as the time any string element takes to move through one complete oscillation. A typical period is marked on the figure 1 also. Now by applying equation 1 on both ends of this time interval, what we get? A typical time period. A typical period is marked on figure 1. Now by applying equation 1 on both ends of the time interval, what we get? We get minus a sine omega 1 t minus ka a sine omega t1 plus t, omega t1 plus omega t. This can be true only if the least value of omega t is 2 pi. This will be true if least value of omega t is 2 pi, or if omega equals to 2 pi upon t. This will be equation 2, we can say. Here omega is called the angular frequency. And this will be vastly different from the regular frequency of the wave, and its SI unit is radian per second. So that's all for today. Next we will talk about the frequency of a wave and the speed of a traveling wave.